Okay, this is video number 4. I'm taking off where I left off on video number 3. So, this is 2 plus or minus the square root of 4 minus 4 times 0.96 all over 2. That turns out to be 2 plus or minus the square root of 0.16 over 2. The square root of 0.16 is 0.4, so that's going to be 2.4 divided by 2 is 1.2, and 2 minus 0.4 is 1.6 divided by 2 is 0.8. So there's our two eigenvalues, 1.2 and 0.8. Now, of course, to graph eigenspaces, we need the eigenvectors, or the basis for that, so we need to substitute for those two eigenvalues. So let's go over here and say, if lambda is equal to 1.2, what will we get? Well, we'll put in 1.2 there. That'll give us negative 0.5, and that'll give us 0.1. So if negative 0.5, 0.1, negative 0.5, and 1.3 minus 1.2 is also 0.1. And, you know, the eigenspace is a null space, so set up the homogeneous equation, it would look like that. These clearly are the same, so this row would zero out, and you're going to get, let's just multiply by negative 10, and that would give us 5, 1, 0, and 0, 0, 0. And of course our free variable is x sub 2. So 5x sub 1 is equal to negative 1. No, I'm sorry, we multiplied by negative. So that would have been a negative there. That should be a positive x sub 2. So x sub 1 is equal to 1/5 x sub 2. And x sub 2 is free. So for lambda equaling 1.2, we get the basis vector 1/5 for x sub 1 and 1 for x sub 2. We could just multiply that by 5 because it's any vector in the eigenspace. That would be 1/5. We could use that as a basis vector also. And then for lambda being equal to 0.8 is the other one. We get 0.7 minus 0.8. I didn't need to write that. 0.7 minus 0.8 is negative 0.1. So negative 0.1 and 0.1 there. Then negative 0.5. And if we plug in 0.8 into here, we get 1.3 minus 0.8 is 0.5. You can clearly see those are linearly dependent, so we'd be able to zero out that. Let's just multiply everything by a negative 10. So we'll just get 1, negative 1, 0, 5, negative 5, 0. And we can see if we subtract 5 of those, this would zero out. And we get x sub 1 minus x sub 2 equals 0. So x sub 1 just equals x sub 2, right? We just add that to the other side. And that gives us, and x sub 2 is free. So we get the vector x sub 2 times 1, 1. And that's our eigenspace for lambda equaling 0.8. So if we just take a little sketch of that, let's do this. We'll just do this mostly in the positive quadrant. We don't really need much of the way of negatives because it's not really realistic. But let's take this and we'll plot 1, 5, and I'll just sketch it. 1, 2, 3, 4, 5. 1, 5. That eigenspace corresponds with the lambda being 1.2. So that's a repeller. That goes away from the origin in both directions. And then for lambda equaling 0.8, we get 1, 1. I'll just put that there. That's about right. And there's for lambda equaling 0.8. Now, oops, I shouldn't have put an arrow on the end because this is an attractor. Lambda is less than 1. So this is going to go into the origin. Okay. So now we can see that any population in this area, these are going to be pushed to the origin from this one and pushed this way from this eigenspace. So this is in this quadrant. an eigenvector, or any vector, it can't cross an eigenspace. If it moves towards the eigenspace, it'll hit it and then run along the eigenspace. If it goes along here, if it tries to cross over an eigenspace, it'll hit it and just go along it. It really can't ever touch it. It just is asymptotic. So any vector in here, it's gonna head this way, and that's gonna be, heads this way from this eigenspace, and then this eigenspace pushes it that way. So we can see it's going towards extinction. Everything over here is going towards extinction, right? We're zeroing out. This is the whale population. This is the salmon population. And this is the salmon population, I might add, in thousands. So this was 1-to-1. That means this was one whale for every 1,000 salmon, is what that means. And if your number of salmons are below this, if you have fewer than if you're one whale and one salmon, it's going to be right on this eigenspace. It'll go to 0. I don't know why that arrow's going that way. It should be that way. All of these, anything on the eigenspace will go to 0. So this is destined for destruction. So any one of these where the salmon is fewer, for one whale, if there's fewer than 1,000 salmon, it's going to extinction. So you have to have, for every whale, you have to have over 1,000 salmon. So you have to have, for every whale, more than 1,000 salmon. And if you do, you'll be moving towards this ratio. Any of these eigenvectors, they might go down this way, but they're going to end up coming back up here. Since this is an attractor and this is a repeller, these will be asymptotic. And similarly even over here, right? Because this pushes them this way, this pushes them towards the origin, but that will push them back out again. And so everything over here, as long as the whale population, if there's more than 1,000 salmon for every whale, as long as the salmon's higher, then you're going to be going towards this ratio, which is, this is one whale, remember this is 1-to-5, that's what this eigenspace was. You're going towards one whale for every 5,000 salmon. That's what the population will tend toward. That's kind of the perfectly sustainable and continued relationship.